Hello. We have seen how the urine is formed through the three steps: glomerular filtration, tubular reabsorption, and tubular secretion. Now let's see in brief how this urine is concentrated. In human beings, we can see that the quantity of glomerular filtrate produced is about 180 liters per day. Though it is so, the quantity of urine excreted is only 1.5 liters per day, which means that normally kidney excretes a concentrated urine to prevent the volume depletion from the body. And the osmolarity of glomerular filtrate is about 300 milliosmoles per liter, which is isotonic to the plasma. And the osmolarity of urine, normally the urine will be concentrated and excreted, so its osmolarity is usually 1200 milliosmoles per liter, and it can range between 30 milliosmoles per liter to 1400 milliosmoles per liter. And this capability of kidneys to pass urine with extremeness of osmolarity, this ability of kidney, is essential for the maintenance of volume and electrolyte homeostasis. The osmolarity of urine depends upon the water content in the body and antidiuretic hormone. See, the mechanism of urine formation is the same for both dilute urine and concentrated urine. But this dilution and concentration of urine depends upon the water content of the body. How a dilute urine is formed? If the water content in the body is high, the secretion of antidiuretic hormone from posterior pituitary will be inhibited, and the reabsorption of water from the renal tubules will be greatly reduced. So, a large amount of water will be excreted through the urine, and this makes the urine dilute. So, how a concentrated urine is formed? When the water content in the body is low, the ADH secretion from the posterior pituitary will be increased, and this causes retention of water by the kidney tubules, and thus a very concentrated urine will be excreted. But the thing is that this mechanism of urine concentration is not so simple as that of dilute urine formation. So this concentration of urine involves two processes, that is development and maintenance of medullary gradient by the countercurrent system and secretion of antidiuretic hormone. So let's see what is medullary gradient. The interstitial fluid in the cortical region is isotonic with that of plasma, having an osmolarity of about 300 milliosmoles per liter. And as this interstitial fluid extends from the outer region to the inner region of medulla, there will be an increasing gradient of osmolarity. So the osmolarity will be maximum at the innermost part of medulla, that is at the tip of the renal papillae, which is about 1200 milliosmoles per liter. This gradual increase in the osmolarity of the medullary interstitial fluid is called the medullary gradient. And this medullary gradient is having an important role in the concentration of urine. Countercurrent mechanism. It is a unique mechanism in the kidney which helps in the concentration of urine. The term countercurrent means flow of fluid in opposite direction in adjacent structures. We have seen the loop of Henle. It has a descending limb and an ascending limb which are adjacent to each other, and the flow of fluid is in opposite direction. So countercurrent mechanism is a system of U-shaped tubules in which the flow of fluid is in opposite direction in two limbs of the U-shaped tubules. Here the countercurrent mechanism involves a countercurrent multiplier and a countercurrent exchange. This countercurrent multiplier is formed by loop of Henle and countercurrent exchange is formed by vasa recta. And this countercurrent mechanism is responsible for the development of medullary gradient and also its maintenance, and the hyperosmolarity of interstitial fluid in the inner medulla. This osmotic gradient is generated by loop of Henle and it is maintained by vasa recta. And the collecting duct acts as the equilibrating device. Thus, the renal countercurrent mechanism depends on the integrated functioning of loop of Henle, vasa recta, and collecting duct. We have seen that the glomerular filtrate formed is isosmotic with that of plasma, having an osmolarity of about 300 milliosmoles per liter. And in the proximal convoluted tubules, majority of the solutes will be reabsorbed, and secondary to this, considerable amount of water will also be reabsorbed. That is, obligatory reabsorption of water happens there, which helps to maintain the osmolarity same as that of plasma. So the fluid passing the proximal convoluted tubule is also isosmotic. So about 30% of this tubular fluid reaches the loop of Henle, and that is isosmotic. Due to the selective reabsorption of solutes and water in the different segments of the loop of Henle, there occurs a higher osmolarity in the medullary interstitium. Let us see how this happens. We have seen earlier that the descending limb of loop of Henle is permeable to water but impermeable to solutes. So what happens when the tubular fluid passes down the descending limb? More and more water will be reabsorbed, but the solutes remain inside the tubule, which means the fluid becomes hypertonic as it descends downwards. Okay, and in the tip of the loop, the fluid becomes highly concentrated such that its osmolarity will become more than the interstitial osmolarity. And when this fluid reaches the thin ascending limb of loop of Henle, this thin ascending limb is passively permeable to solutes but impermeable to water. So what happens? Water cannot be reabsorbed from that segment, but some amount of solutes will be passively reabsorbed. Okay. So every time this tubular fluid passes through the thin ascending segment, extra solutes enter the interstitium. Okay. So this helps in multiplication of the interstitial osmolarity. The tubular fluid now reaches the thick ascending limb of loop of Henle. We know that thick ascending limb is impermeable to water but permeable to solutes. Okay, so here the active transport of solutes happens. See, the sodium ions and chloride ions will be actively transported from this segment into the interstitium. We know that there are one sodium, one potassium, two chloride transporters in the luminal membrane and sodium potassium pump in the basolateral membrane. So due to the activity of these pumps, these solutes will be actively reabsorbed from the tubular fluid into the medullary interstitium, and since it is impermeable to water, what happens? Water will be retained inside the tubule, but solutes will be reabsorbed. This reabsorption of solutes into the medullary interstitium helps to build up the interstitial osmolarity, but the solution or the fluid inside the tubule will become hypotonic. Why? The water will be retained inside the tubule, but more and more solutes will be removed from it. So thus it becomes hypotonic. The fluid was hypertonic at the tip of the loop, but after passing through the thin ascending limb, some of the solutes will be reabsorbed passively, and here in the thick ascending limb, active reabsorption occurs, and more solutes will be added into the interstitium from the fluid without reabsorption of water, which means that it becomes a hypotonic solution. Due to the movement of solutes from the thick ascending limb of loop of Henle, there occurs an osmotic gradient at any level of loop of Henle. So the process in which a small osmotic gradient established at any level of Liouville is multiplied into a larger gradient is called countercurrent multiplication system, and Liouville acts as a countercurrent multiplier. We can see that as this tubular fluid descends downwards into the deeper layers of medulla, it becomes more and more concentrated, and thus the osmotic gradient produced will be increased. So this increase in the osmotic gradient along the axis of this loop is called axial gradient. And this axial gradient is dependent on the length of loop of Henle. That is, longer the loop of Henle, greater will be the axial gradient. We know that there are two types of nephrons, cortical nephrons and juxtamedullary nephrons. And juxtamedullary nephrons are having longer loop of Henle. So the higher osmolality is built only in the medullary interstitium because of this longer loop of Henle of juxtamedullary nephrons. This is because as the length increases, there occurs more chance for the reabsorption of solutes from the thick ascending limb of loop of Henle. See, the sodium ions and chloride ions can either be passively reabsorbed from the thin ascending limb and or actively reabsorbed from the thick ascending limb. And if the length is more, there will be more absorption of solutes from this ascending limb. So it creates a higher osmotic gradient. So as the length increases, the osmotic gradient produced will also be increased, and this accounts to the higher osmolality in the medullary interstitium. Role of collecting duct in concentration of urine. Collecting duct acts as an osmotic equilibrating device. See, it contributes to the concentration of urine in two ways. One is by its permeability to water, and the second is by its permeability to urea. We know that the tubular fluid, after passing through the thick ascending limb of loop of Henle, has become hypotonic. And this hypotonic fluid, when reaches the collecting duct, in the presence of ADH, it will move out of the tubular fluid. That is, much amount of water will be reabsorbed from the collecting duct. So this makes the tubular fluid hypertonic. Okay. Much amount of water will be removed from the tubular fluid means it becomes hypertonic. So that is uh, the urine concentration by its permeability to water. Second method is by its permeability to urea. See, um, some amount of urea is reabsorbed in the proximal convoluted tubule from the glomerular filtrate. And then as it passes through the nephron, what happens is that some portion of urea will be secreted into the tubular fluid in the descending limb of loop of Henle. So in the medullary part of the collecting duct, this tubule is permeable to urea. So other than this medullary collecting duct, rest of the tubules become relatively impermeable to urea. See, in the proximal convoluted tubule, some part of urea will be reabsorbed and rest of the tubule will be impermeable to urea other than medullary part of collecting duct. And some part of urea will be secreted into the tubular fluid in the descending limb of loop of Henle. So what happens? The concentration of urea in this tubular fluid increases by the time it reaches the medullary part of collecting duct. So this higher concentration of urea in the tubular fluid causes a passive movement of urea into the interstitium from the medullary part of collecting duct. So this facilitated diffusion of urea occurs via urea transporters, and this accounts for the increase in hyperosmolarity of the medullary interstitium. So this facilitated diffusion of urea is followed by the movement of water from the tubular fluid into the interstitium in order to maintain the osmotic balance. So this causes a concentration of urine. Okay. So this is the role of collecting duct in concentrating the urine. Now, vasa recta, the countercurrent exchanger. This vasa recta is responsible for the maintenance of the medullary gradient. So this vasa recta is also a U-shaped tubule with a descending limb, hairpin bend, and an ascending limb. And the direction of the fluid movement is opposite in both the limbs, in both the descending limb and the ascending limb. So this vasa recta forms a countercurrent system having the two limbs adjacent to each other and the movement of the fluid is in opposite direction. Okay, so that forms a countercurrent system. And this vasa recta runs parallel to the loop of Henle, and the direction of movement of fluid in the vasa recta is in a direction opposite to the movement of fluid in the loop of Henle. See, the descending limb of this vasa recta runs along the ascending limb of loop of Henle, and the ascending limb of vasa recta runs along the descending limb of loop of Henle. Got it? So here we can see that vasa recta forms a countercurrent mechanism because of its positioning of the descending and ascending limbs, and it runs parallel to the loop of Henle, and the movement of fluid is in a direction opposite to that of the movement of fluid in the loop of Henle. Okay. Role of vasa recta in concentrating the urine. In the descending limb of vasa recta, the water diffuses out of the vessels and solute diffuse into the vessels. And in the ascending limb, water diffuses into the vessels and solutes diffuses out of the vessels. That is, the water and solutes move in direction opposite to each other. So we can see that from the thick ascending limb of loop of Henle, the solutes are reabsorbed into the medullary interstitium. And from there, these solutes diffuse into the descending limb of vasa recta. Simultaneously, water will diffuse out of the descending limb into the medullary interstitium. So as the blood flows slowly through the vasa recta, a large quantity of solutes will be accumulated in the descending limb of this vasa recta. And by the time it reaches the ascending limb of vasa recta, the concentration of the solutes will be much higher. And this causes the diffusion of these solutes into the medullary interstitium. So this diffusion of solutes back into the medullary interstitium is accompanied by the movement of water from medullary interstitium into the ascending limb of vasa recta. So we can see that the solutes that are reabsorbed from the thick ascending limb of loop of Henle enters the descending limb of vasa recta and are diffused back into the medullary interstitium from the ascending limb, and the water that is diffused out of the descending limb is taken back by the ascending limb and carried away with it along with the blood to the cortex. Thus, the solutes are recirculated in the medulla, which accounts for the hyperosmolality of the medullary interstitium. See, these solutes are not carried away with the blood. They are being recirculated in the medulla, whereas the water is being removed or carried away along with the blood. So this accounts to the hyperosmolality or hypertonicity of the medullary interstitium. The reabsorption of urea also accounts to this. See, um, from the medullary interstitium along with other solutes, urea is also reabsorbed or diffused, enters the descending limb of the vasa recta, and as the blood passes through the ascending limb of vasa recta along with other solutes, this urea is also diffused back into the medullary interstitium. So this urine is also being recirculated repeatedly in the medullary interstitium, which accounts to the hypertonicity of medullary interstitium. Okay, so this is the role of vasa recta in maintaining the hyperosmolarity. We can see that the water that is removed from the descending limb of loop of Henle is taken back by the ascending limb of vasa recta, is carried away by the ascending limb of vasa recta. Water that is diffused from the descending limb of vasa recta as well as the water that is diffusing out of the descending limb of loop of Henle, both are carried away by the ascending limb of vasa recta. And the solutes that are reabsorbed from the thick ascending limb of loop of Henle are taken by the descending limb of vasa recta and are diffused back from the ascending limb of vasa recta into the medullary interstitium so that the solutes are not lost from the medullary interstitium. Okay, so we can see that the tubular fluid, while passes through the thin segment, some solutes are being passively added into the medullary interstitium, and while passing through the thick segment, solutes are reabsorbed by active reabsorption. And these solutes will enter the descending segment of the vasa recta, and by the time it reaches the ascending segment of vasa recta, it will diffuse back into the interstitium in order to maintain the osmolarity of medullary interstitium. And the water that is secreted by the descending limb of loop of Henle as well as the descending limb of vasa recta are carried away by the ascending limb of vasa recta, and these all accounts to the maintenance of hypertonicity of the medullary interstitium. For better understanding, let us recollect the slides role of loop of Henle and role of vasa recta in urine concentration. The descending limb of loop of Henle is highly permeable to water, which means water will diffuse out of descending limb and it is impermeable to solutes. Thin ascending limb of loop of Henle is relatively impermeable to water and passively permeable to solutes. That is, some amount of solutes will be reabsorbed from the thin ascending limb. The thick ascending limb of loop of Henle is completely impermeable to water and permeable to solutes, where the active transport of solutes occur. Adjacent to the thick ascending limb of loop of Henle lies the descending limb of vasa recta, where the water diffuses out of the vessels and solutes diffuse into the vessels. And the ascending limb of vasa recta lies adjacent to the descending limb of loop of Henle, and here the water diffuses into the vasa recta and solutes diffuses out of the vessels. Here we can see that the water that is diffused out of the descending limb of loop of Henle are taken away by the ascending limb of vasa recta into the cortex. That is, the water that is diffused out of the loop of Henle is removed from the medullary interstitium, thereby increasing the osmolarity of medullary interstitium. Likewise, the water that is uh, diffused by the descending limb of vasa recta is being reabsorbed by the ascending limb of vasa recta and carried away from the medullary interstitium. So it helps in maintaining the hyperosmolarity. Likewise, the solutes that are reabsorbed from the thick ascending limb of loop of Henle are being taken by the descending limb of vasa recta and are released into the medullary interstitium by the ascending limb of vasa recta, which means there occurs a constant recirculation of solutes in the medullary interstitium. The solutes like sodium, chloride, urea, etc. are being constantly recirculated in the medullary interstitium, which helps in the maintenance of hyperosmolarity of medullary interstitium. So this is achieved by vasa recta. And we can see that the reabsorption of sodium and chloride ions occur from the thicker ascending limb, and that is constantly being given back into the medullary interstitium. In the thin ascending limb of lipofenily, there occurs some passive reabsorption of solutes. So every time the fluid passes the thin ascending limb of lipofenily, extra solutes are being added into the medullary interstitium, which accounts to its hyperosmolality. Apart from this, there is regular addition of more and more solutes into the descending limb of lipofenily by constant glomerular filtration. We know that glomerular filtration is a constantly ongoing process, and um, more solutes will be added into the descending limb as the tubular filtrate reaches the descending limb. So the reabsorption of solutes from the thick ascending limb, the passive reabsorption of solutes from the thin ascending limb, and the addition of new solutes by the filtrate into the descending limb. All these together increases or multiply the osmolarity of medullary interstitial fluid, and thus the medullary gradient, and hence it is called countercurrent multiplier. Thus lipofenily acts as the countercurrent multiplier. And for the solutes, sodium chloride and urea, the water is exchanged. The solutes are exchanged for water between the ascending and descending limbs of vasa recta, and hence this system is called as countercurrent exchanger, and vasa recta acts as the exchanger here. Thus lipofenily helps in creating the osmotic gradient of medullary interstitium, and vasa recta helps in maintaining the osmotic gradient of medullary interstitium. Okay. Role of antidiuretic hormone in concentrating the urine. The final concentration of urine is achieved by the action of antidiuretic hormone. We know that normally the distal convoluted tubule and collecting duct are impermeable to water, but in the presence of ADH, these segments become permeable to water, resulting in the reabsorption of water from distal convoluted tubule and collecting ducts into the medullary interstitium. So this water reabsorption induced by ADH is called as facultative reabsorption of water, and thus a large quantity of water is removed from the tubular fluid while passing through the DCT and collecting duct, and thus the urine becomes hypertonic with an osmolarity of about 1200 milliosmoles per liter. So when we look into the whole process of urine concentration, we can see that the glomerular filtrate, when passes through the different segments of the renal tubules, it undergoes various changes in its osmolarity. In the Bowman's capsule where the glomerular filtrate is formed, it is having the same composition as that of plasma except in proteins. So it remains isosmotic to plasma, having an osmolarity of about 300 milliosmoles per liter. When it reaches the proximal convoluted tubule, active reabsorption of solutes followed by obligatory reabsorption of water occurs there, and hence the osmolarity remains the same, isosmotic to plasma, that is 300 milliosmoles per liter. And then it reaches the descending limb of lipofenily. There passive diffusion of water occurs, so it increases the osmolarity of the tubular fluid. So as the descending limb goes deeper and deeper into the medulla, the osmotic gradient increases. The osmolarity of this tubular fluid increases, and it reaches a maximum by the time it reaches the tip of the loop of Henle, that is about 1200 milliosmoles per liter. So this fluid becomes hypertonic to plasma, and then it enters the thin ascending segment of loop of Henle where some passive reabsorption of solutes occur. So its osmolarity decreases from 1200 to 1000, then 800, then 600, like that. And by the time it reaches the thick ascending segment, active reabsorption of solutes occur, so that its osmolarity further decreases and it ranges between 150 to 250 milliosmoles per liter. Thus, this fluid becomes hypotonic to plasma by the time it reaches the distal convoluted tubule. So, the distal convoluted tubule and collecting duct are usually impermeable to water, but in the presence of ADH, they become permeable to water, resulting in water reabsorption and final concentration of urine. So the reabsorption of large quantity of water increases the osmolarity of fluid gradually, and when the urine leaves the medullary part of the collecting duct, its osmolarity reaches the maximum of about 1200 milliosmoles per liter. Thus, urine becomes hypertonic to plasma. Thus, it becomes clear that an osmolarity of 1200 to 1400 milliosmoles per liter is maintained in the deepest portion of medullary interstitium, and this higher osmolarity in the interstitium helps in the concentration of urine. So that is all about the urine concentration. Thank you for your listening.